Welcome, dear listener, to Dreams of Gravity. If you're here right now, chances are the day is winding down. Maybe the lights are low, maybe the world outside has grown quiet, or maybe you've simply been waiting for a moment like this. A moment to breathe, to let go, and to drift somewhere far beyond the ceiling above you. Perhaps you've had a long day. Perhaps the kind of day where the mind kept running, kept circling the same thoughts like a satellite that can't quite escape its orbit. That's all right. You don't need to resolve anything tonight. You don't need to arrive at any conclusion. The day is done, and it belongs to the past now, and the past is a very gentle place. It can't demand anything from you anymore. Before we begin, I'd like to invite you to do something simple. Find your most comfortable position. If you're lying in bed, let your body sink a little deeper into the mattress. Feel the weight of your arms, your legs, your shoulders, and let that weight go. You don't need to carry anything right now. If you're sitting, let your hands rest gently in your lap, unclenched, open. Close your eyes if you like, or let them go soft and unfocused. There's nothing you need to watch. There's nothing you need to do. Take one slow breath in through your nose. Fill your lungs completely. Let your chest and your belly expand. Hold it just for a moment and let it out, slowly, all the way, until your lungs are quiet and still. Feel your shoulders drop. Feel the small muscles around your eyes soften. Feel the space between your eyebrows relax. Good. You're already there. Take another breath if you like. There's no rush. This whole journey is unhurried. The universe has been here for nearly 14 billion years. It can wait a few more seconds while you settle in. Tonight, we're going to travel together. Not to any place you could find on a map. Not to any destination with a name you'd recognize from a travel guide or a headline. We're going somewhere much older than names, much wider than maps. We're going to the edge of what we know, and perhaps a little beyond. We're going to talk about Saturn and its rings, and a discovery so quiet and so profound that it feels almost like watching something beautiful fade in slow motion. The way a sunset fades, the way the last note of a piece of music fades, with a kind of aching grace. We're going to talk about the universe itself, its galaxies and stars, its black holes and nebulae, its sense of time that makes our entire civilization feel like a single breath in a very long night. And along the way, I hope you feel something settle inside you. Not excitement. We're not here for excitement tonight. Something quieter. The particular kind of peace that comes from remembering how large everything is, how ancient, how patient. The kind of peace that arrives when you realize that, in the context of all of this, all the billions of years, all the trillions of stars, your worries, as real as they are also very, very small. And smallness, in this context, is not a diminishment. It's a relief. So settle in. Let your thoughts become gentle. If a worry drifts past, just let it go. Like a leaf on a slow river, moving on, finding somewhere else to be. You'll deal with everything you need to deal with, just not right now. Right now, you're traveling. We'll begin, as all good journeys do, with something you can almost see. Step outside on a clear night, any season. And if you're away from city lights, if you're somewhere in the countryside where the sky goes all the way down to the horizon uninterrupted, you might catch it. A pale, creamy smear of light arching across the sky, like a brushstroke on dark velvet, like someone dragged a fingertip through a jar of pale luminescence and swept it coast to coast across the darkness. That is the Milky Way. That is our home. And it is, by any reasonable measure, incomprehensibly vast. Our galaxy stretches roughly 100,000 light-years from edge to edge. A light-year is the distance light travels in a single year, moving at about 300,000 kilometers every second. That's fast enough to circle the entire Earth more than 7 times in one heartbeat. Fast enough to travel from the Earth to the Moon in just over 1 second. Fast enough to reach the Sun in about 8 minutes. And yet, at that speed, it would still take 100,000 years to cross our galaxy from one side to the other. 100,000 years of traveling at the fastest speed anything in the universe can move, and you'd barely have crossed your own neighborhood of the cosmos. Inside this galaxy, there are somewhere between 200 and 400 billion stars, perhaps more. Scientists are still counting, still refining, still finding new ones tucked away in dusty corners of the spiral arms, hidden behind veils of gas and ancient dust. Each of those stars is a sun, some smaller and cooler than ours, burning a deep, slow red for trillions of years, patient and dim. Some larger and hotter, blazing brilliant blue-white and burning themselves out in just a few million years, like candles that shine too bright too fast, spending their fuel in a brilliant extravagance and then collapsing into darkness. Our own sun sits about halfway out from the center of the Milky Way, in a quieter region sometimes called the Orion Arm, one of the spiral arms of the galaxy, named not because Orion is nearby, but because the constellation, as we see it, lies roughly in that direction. The Sun is a fairly average star, nothing too dramatic about it, at least not by cosmic standards. No blue supergiant with a dramatic destiny. No ancient red dwarf marking time in geological quiet. Just a steady, middle-aged yellow-white star that has been burning hydrogen into helium in its core for about 4.6 billion years, and has roughly another 5 billion years left before it begins to change. Before it swells into a red giant, expanding outward, engulfing Mercury, then Venus, then perhaps the Earth itself, and then, after that expansion, slowly shedding its outer layers and cooling into a white dwarf. A stellar ember, cool and quiet, remembering nothing. But we're getting ahead of ourselves. There's a long, long story to tell before we reach endings. And right now, in this moment, I find myself curious about you, the person listening to this, wherever you are. By the way, I wonder, where are you watching from tonight? Which city and what time of day is it for you right now? Are you somewhere cold with rain tapping against the window or frost building on the glass? Or somewhere warm with a fan humming in the corner and the night air carrying the smell of something green? I love thinking about all the different places these words might reach. Someone in a quiet apartment with the city humming below. Someone in a house on a hill where the silence is almost total. Someone in a different time zone entirely, watching the dawn come while for someone else, it's the deep middle of the night. Whatever your world looks like right now, whatever the weather, whatever the season, whatever is waiting for you tomorrow, I'm glad you're here. Now, let's talk about Saturn. Of all the planets in our solar system, Saturn is the one that most looks like a dream. Even through a modest backyard telescope, the kind you might find at a department store, assembled in a living room on a winter afternoon, the sight of it stops people mid-breath. It has stopped people mid-breath for centuries. A pale golden sphere, luminous and unhurried, surrounded by a flat, impossibly elegant system of rings. Rings that seem too perfect to be real, too symmetrical to have happened by accident, too beautiful to be merely physics. And yet, there they are, physics being beautiful, which it does often when we look closely enough. Saturn is the 6th planet from the Sun, and it is enormous. Its diameter is about 9 times that of Earth. If Earth were the size of a grape, Saturn would be the size of a basketball. It's a gas giant, meaning it has no solid surface, at least not in any way we'd recognize. Would simply sink. The atmosphere growing would simply sink. The atmosphere growing thicker and hotter and more pressurized around you with every kilometer, until you were crushed and dissolved long before you reached whatever dense, strange core might exist at the center. Some models suggest Saturn may have a solid or semi-solid core of rock and metal, squeezed by unimaginable pressure into a state of matter that barely has a name. Saturn is mostly hydrogen and helium, the two simplest and most abundant elements in the universe. The same elements that filled the early universe just minutes after the Big Bang. In a very literal sense, Saturn is made of primordial stuff, the raw material of the cosmos, shaped by gravity into a sphere and set spinning. And it spins remarkably fast. Saturn completes one full rotation in just about 10.5 hours. For comparison, Earth takes 24 hours. So a day on Saturn, if such a concept can apply to a planet with no surface, is less than half the length of ours. This rapid spin causes it to bulge slightly at the equator and flatten at the poles. Not a perfect sphere, but a shape that physicists call an oblate spheroid. The equatorial diameter is notably larger than the polar diameter. Even Saturn's shape is gentle and rounded, like a stone worn smooth by a very slow river, like a word softened by long use. Saturn's atmosphere shows bands of color, pale yellows and creamy whites, subtle golds and occasional hints of brown, driven by enormous jet streams and atmospheric circulation patterns. Near the North Pole, there is something even stranger, a persistent hexagonal storm system, a geometric pattern in the clouds, a 6-sided structure larger than the Earth itself that has been rotating steadily for as long as we've had instruments to observe it. A hexagon made of weather, mathematics expressing itself in the atmosphere of a distant world. And then there are the rings. Saturn's rings are made mostly of water ice, fragments ranging from the size of a grain of sand to the size of a house, and occasionally larger, all orbiting the planet in thin, flat bands. The ice is extraordinarily pure in places, bright and reflective, catching the distant sunlight and scattering it back across space. Mixed in with the ice are trace amounts of rocky material, silicate dust, organic compounds, the ingredients that drift through the solar system, remnants of ancient collisions and cometary showers. From a distance, the rings look solid and seamless, like a vinyl record, like a halo made of light. But up close, they are a vast, glittering cloud of individual pieces, each one following its own orbit around Saturn, each one a tiny world of frozen water tumbling slowly through space. Between the major rings, there are gaps, cleared by the gravitational influence of Saturn's moons, which shepherd the ring material into channels and divisions with remarkable precision. The most prominent of these gaps is called the Cassini division, a dark gap between the A ring and the B ring, about 4,800 kilometers wide, visible even through a modest telescope. Huygens saw it. Galileo, with his crude instrument, probably did not. The rings stretch outward nearly 300,000 kilometers from Saturn's equator. That's almost the distance from the Earth to our moon. And yet, for all their breadth, they are extraordinarily thin. In most places, only about 10 meters thick. 10 meters. The height of a 3-story building. Imagine a structure as wide as the distance to the moon, as thin as a small building. So if the rings were scaled to the proportions of a piece of paper, the same ratio of thickness to width, that paper would need to be proportionally thinner than the finest razor blade ever manufactured. A structure that wide, that thin, that dynamically maintained against all the forces trying to disrupt it. It is one of the most elegant things in the known solar system. For a long time, astronomers assumed the rings were ancient, as old as Saturn itself, a relic from the formation of the solar system 4.5 billion years ago. It seemed logical, almost inevitable. Saturn is old. The rings are there. The solar system is old. Surely they all came together at the beginning. This assumption sat comfortably in textbooks for decades, unchallenged in any meaningful way, simply because we hadn't looked closely enough to challenge it. But something kept nagging at the edges of that assumption. The rings are bright, brilliantly, almost impossibly bright, reflecting about 80% of the sunlight that hits them. If they were ancient, they should have darkened over time, accumulating dust and debris from meteorite impacts and the general cosmic grime that fills interplanetary space. Space is not empty. It is full of dust, of micrometeorites, of charged particles from the solar wind. Ancient ice goes grey, the way old snow goes grey on the sides of roads. Ancient ice gets dirty, but Saturn's rings are white, clean, almost new-looking in cosmic terms, like fresh snow rather than old drifts. This discrepancy was noticed. Quietly, for years, it was noticed. Then came the data from Cassini. Cassini was a spacecraft launched by NASA and the European Space Agency in October of 1997, on a journey that would take it to Saturn and keep it there for 13 extraordinary years. It was one of the most successful deep space missions ever flown, returning hundreds of thousands of images and measurements that transformed our understanding of the ringed planet and its extraordinary collection of moons. In 2017, in a planned and deliberate finale called the Grand Finale, Cassini was guided into Saturn's atmosphere, where it burned up and became part of the planet it had spent so long orbiting, ensuring it could never contaminate the potentially life-bearing moons it had discovered, like Enceladus with its plumes of water vapor, or Titan with its seas of liquid methane. Before it ended, though, Cassini did something that had never been done before. During its final months, it flew through the gap between Saturn's innermost ring and the top of the planet's atmosphere, a region only about 2,000 kilometers wide, a gap that had always seemed too risky, too unknown to enter safely. No spacecraft had ever gone there. The first time Cassini made that crossing, mission controllers held their breath, waiting for the signal confirming it had survived. It had. And from that intimate vantage point, closer to Saturn than any spacecraft had ever been, it measured something unexpected. Material from the rings was falling into Saturn, falling inward, spiraling down through the magnetic field lines, raining onto the planet's upper atmosphere in a slow, continuous drizzle. Scientists called it ring rain, and when they calculated the rate, how much material was falling, how fast. The numbers were startling. The rings were losing mass at a rate of between 4 and 23,000 kilograms per second. Every second, thousands of kilograms of ring material was being lost, pulled down by Saturn's gravity, drawn along magnetic field lines, carried into the atmosphere where it would mix and dissolve and become part of the planet. Water molecules, ionized by sunlight, losing their charge and falling inward. A slow, quiet dissolution. At that rate, if it had been happening for 4.5 billion years, the rings would have been gone long ago. The math is clear. They wouldn't exist, and yet they do. So the numbers pointed in only one direction. The rings are young, cosmically young, formed somewhere between 10 and 400 million years ago, not at the birth of the solar system, but long after, in what is, by geological standards, the relatively recent past. Perhaps around the time the dinosaurs were walking the Earth, or perhaps even more recently than that. This was a revelation, quiet, as scientific revelations often are, announced in a journal paper, discussed at conferences, slowly absorbed into the consensus, but profound. And it raised a beautiful, melancholy question that I keep returning to. If the rings are young and they are disappearing, where are we in their story? According to current estimates, Saturn's rings will be entirely gone within another 100 million years, perhaps significantly less. In the vastness of cosmic time, that's a very short window. The universe is 14 billion years old. 100 million years is less than 1% of that. It's a narrow band of time, a brief chapter. But to us, to creatures who measure our lives in decades, 100 million years sounds like safety, like permanence, like forever. And in a human sense, it is. Our great-great-grandchildren will see rings. Their descendants, stretching forward for millions of generations in an optimistic telling of our story, will still see rings. But eventually, there will come a night when an astronomer, or perhaps just a curious person with a telescope, points it at Saturn and sees something different. A plain sphere, pale gold, unmarked by any halo. The rings will be gone. Not in a dramatic moment, not a collapse or an explosion or a visible change, but in a slow, patient dissolving, a long exhalation until there is simply nothing left to catch the light. We exist at a very specific, very unusual moment in Saturn's history. We are here in these brief human lives while the rings still exist, and that, I think, is worth sitting with for a moment. That particular grace of timing. We didn't earn it, we didn't plan it, but here we are, in the window. Let's drift for a moment from Saturn's rings into something even wider, into the ocean of space that holds Saturn and Earth, and everything we've ever known or loved or wondered about. The universe is approximately 13.8 billion years old. That number is almost impossible to feel directly. The human brain didn't evolve to feel billions of years. In the same way, it didn't evolve to feel the speed of light or the scale of galaxies. But here's one way to try. If you compressed the entire history of the universe into a single calendar year, 1 year, January through December, then the Big Bang would happen at midnight on January 1st. The Milky Way galaxy would form in mid-March. Our Sun and solar system would coalesce in early September, forming from a cloud of gas and dust and ancient stardust. The first simple life on Earth would appear in mid-September, single-celled organisms in warm, shallow seas. Complex multicellular life wouldn't appear until mid-December. The dinosaurs would arrive on Christmas Day and go extinct on December 30th. All of human civilization, every empire, every invention, every war, every work of art, every song ever sung, every person who ever lived and loved and lost and wondered at the stars would fit into the last 14 seconds of December 31st. 14 seconds. That is us. That is history. That is everything with a name. And in those 14 seconds, we looked up at the sky and began to ask questions. One of the questions we asked was, what are those faint smudges of light between the stars? For a long time, astronomers catalogued them and called them nebulae, clouds, and assumed they were nearby gas structures within our own galaxy. Then, in the early 20th century, a quiet but momentous debate came to a head. Edwin Hubble, working at the Mount Wilson Observatory in the mountains above Pasadena, California, in the 1920s, measured the distance to one of those smudgy patches, the Great Andromeda Nebula, as it was then called. He did this using a type of star called a Cepheid variable, which pulsates at a rate directly related to its luminosity. By measuring the pulsation period, you can calculate how bright the star actually is, and by comparing that to how bright it appears in the sky, you can calculate the distance. The math was elegant, and the result was staggering. Andromeda was not a nearby gas cloud. It was nearly 2 million light-years away, far beyond the edge of the Milky Way, far beyond anything we had imagined was out there. It was an entire other galaxy, a vast, separate island of hundreds of billions of stars, floating in the void like another universe unto itself. The universe, in a single measurement, became enormously, suddenly larger. Today, we know that the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, contains roughly 2 trillion galaxies. 2 trillion, each containing hundreds of billions of stars. Each star, potentially, with its own system of worlds. The possible number of planets in the observable universe is a number so large it has no practical meaning in ordinary language. It is written with exponents and discussed in abstractions. And yet, each of those trillions of worlds is specific. Each has its own character, its own atmosphere, or lack of one, its own history of impacts and volcanoes, and perhaps, in some cases, chemistry becoming biology, becoming something that wonders about its own existence. We don't know how many harbor life. We don't know if it's just us, lonely and improbable, or trillions of inhabited worlds quietly going about their business in galaxies we'll never visit. We don't know yet, but we're looking, and the looking itself feels meaningful. Hubble also discovered something else, equally world-altering. When he measured the light from distant galaxies, he found that nearly all of them showed a shift toward the red end of the spectrum. A Doppler effect, the same phenomenon that makes a passing ambulance's siren drop in pitch as it moves away from you. This red shift meant the galaxies were moving away from us. Not just a few of them, almost all of them. And the further away a galaxy was, the faster it was receding. The universe is expanding, not the galaxies moving through a fixed space, but space itself stretching, like the surface of a balloon being inflated, carrying the galaxies with it like dots drawn on the rubber. Every region of space is getting slightly larger every moment. The distances between galaxies are growing. The universe is not a static place. It is a dynamic, evolving, expanding structure. and it has been expanding since the very first fraction of a second after the Big Bang. This expansion, discovered in the 1920s, was one of the most transformative realizations in the history of science. Because if everything is moving apart now, then running the clock backward, everything was once closer together. Run it back far enough, 13.8 billion years, and everything in the observable universe was compressed into an extraordinarily hot, dense state, smaller than the period at the end of this sentence. And from that state, in an event we call the Big Bang, everything expanded outward, not an explosion in space, space itself expanding. The difference is subtle but important. There was no pre-existing void into which the universe expanded. Space itself came into being and grew. The universe didn't expand into anything. It simply became larger and continues to do so. And here is something even stranger, discovered only in 1998. The expansion is accelerating. Galaxies are not just moving apart. They are moving apart faster and faster over time. Is not detectable directly. We infer its is not detectable directly. We infer its existence from the observed acceleration alone. And yet, it appears to constitute approximately 68% of the total energy content of the universe. 68% of everything, and we have no idea what it is. Dark matter adds another 27%. Dark matter is matter. It has mass, it exerts gravitational pull, it shapes the rotation of galaxies and the structure of galaxy clusters. But it neither emits nor absorbs light. We cannot see it. We cannot touch it. We know it's there because without it, the math doesn't work. Galaxies rotate at speeds that should tear them apart if ordinary matter were all they contained. Something invisible is holding them together. We call it dark matter because, again, we don't know what it is. So when you add it up, dark energy plus dark matter makes up approximately 95% of the universe. Everything we have ever seen, every star, every planet, every galaxy, every nebula, every atom in every human body that has ever existed, is roughly 5% of the universe. The rest is dark and mysterious and waiting to be understood. This is not a failure of science. It is the frontier of it. It is the place where knowledge ends and wonder begins, which is perhaps the most honest and most exciting place to be. Let's talk now about something that lives at the heart of many galaxies, including our own. Black holes are among the strangest and most fascinating objects the universe has produced. They are regions of space where gravity has become so extreme that nothing, not matter, not radiation, not light itself, can escape once it passes a certain boundary. They are not holes in the traditional sense. They are not empty. They contain an extraordinary amount of mass compressed into an extraordinarily small space. In some cases, a mass of millions or billions of suns compressed into a region smaller than our solar system. The most common type of black hole forms when a massive star dies. During most of a star's life, two forces are in constant balance. Gravity, pulling inward, trying to collapse the star, and the outward pressure generated by nuclear fusion in the core, where hydrogen is being converted to helium and releasing vast amounts of energy. This balance is stable, sometimes for billions of years, but eventually the fuel runs out, the fusion stops, the outward pressure drops, and in a fraction of a second, gravity wins. The outer layers of the star collapse inward with catastrophic speed. The implosion is so violent that it bounces off the increasingly dense core and blows the outer layers into space in one of the universe's most energetic events, a supernova. For a brief time, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. And at the center of that explosion, if the original star was massive enough, what remains is a black hole. At the center of a black hole is a singularity, a point where all the mass is concentrated, where density becomes theoretically infinite, where the equations of physics as we understand them cease to give meaningful answers. It's one of those places where our knowledge ends, and we write, as old cartographers did at the edges of known maps, "Here be dragons." Around the singularity is the event horizon, the boundary of no return. It's not a physical surface you could touch or see, but a mathematical threshold. Cross it, and the geometry of space-time curves so severely that all paths forward, all possible futures, lead inward toward the singularity. There is no direction that leads out. It's not that the gravity is pulling you inward. It's that all of space-time is pointing inward, the way all of time on Earth points forward. You can't go back in time. Inside a black hole, you can't go outward. The directions have swapped. From a safe distance, a black hole looks like an absence in the stars, a dark region, perfectly circular, where the stars behind it have been blocked. But around that absence, light bends. Starlight that passes close to the event horizon gets curved by the intense gravity, bent around the black hole like light through a lens, a phenomenon called gravitational lensing. What this creates, for an observer at the right angle, is a ring of light around the darkness, a glowing halo of photons that have been bent into circular paths, some of them having orbited the black hole multiple times before reaching your eye. This predicted image was confirmed in 2019 when the Event Horizon Telescope collaboration, a global network of radio telescopes linked together to create a virtual telescope the size of the Earth, produced the first direct image of a black hole. The target was a supermassive black hole at the center of a galaxy called M87, about 55 million light-years away, and containing a mass of about 6.5 billion suns. The image showed exactly what theory had predicted: a bright, asymmetric ring of glowing material surrounding a dark central region. It was blurry by photographic standards. The resolution of the instrument was pushed to its absolute limit. But it was real, and it was exactly right. In 2022, the same collaboration published the first image of our own galaxy's central black hole. Sagittarius, a star, 4 million solar masses, 26,000 light-years away. Smaller than M87's black hole, and harder to image because the material around it moves much faster, changing on timescales of minutes rather than days. But it, too, showed the same ring structure, the same dark heart surrounded by light. We orbit it. Our Sun orbits Sagittarius, a star on a journey that takes between 225 and 250 million years to complete. The last time the Sun was at this position in the galaxy, no mammals existed, no flowering plants. The entire age of mammals, every cat, every whale, every bat, every elephant, every human, fits inside a single galactic year with room to spare. There is something about that fact that quietly reorganizes the sense of importance, not diminishing it, just gently relocating it. We are brief passengers on a very long journey, and the journey itself is magnificent. Now let's drift toward the spaces between the stars, toward the clouds and colors that fill the galaxy's quiet corridors. A nebula is made of gas and dust, mostly hydrogen, with helium and traces of heavier elements mixed in. These clouds exist throughout the galaxy, sometimes spanning hundreds of light years, slowly drifting, slowly mixing with the interstellar medium. Under certain conditions, a nearby supernova sending a shockwave through the gas, or simply the accumulation of enough material in one region, the clouds begin to collapse under their own gravity. As they collapse, they fragment, and each fragment collapses further, heating up as it does, the way compressed air heats up in a bicycle pump. Eventually, the cores of those collapsing fragments reach temperatures of millions of degrees, and nuclear fusion begins. A new star is born. The Orion Nebula, which you can find with the naked eye on any clear winter night as a faint smudge in Orion's sword, is one of the most active stellar nurseries in our galaxy. It's about 1,300 light-years away and roughly 24 light-years across. Inside it, hundreds of new stars have formed in the last million years, and more are forming now. Some of them are surrounded by disks of material, the raw ingredients for future planetary systems. Perhaps in 1 billion years, some of those newborn stars will have warm, rocky planets orbiting in the right conditions. Perhaps in 4 billion years, something on one of those planets will look up. Nebulae also form at the end of stellar lives. When a star like our Sun exhausts its hydrogen fuel and expands into a red giant, it eventually sheds its outer layers in a slow wind, a stellar exhalation lasting thousands of years. The shed material forms an expanding shell around the cooling core, illuminated by ultraviolet radiation from that core, glowing in colors determined by the elements present. Hydrogen glows red. Oxygen glows green and blue. Sulfur glows deep red and orange. The result is a planetary nebula, a glowing, symmetrical bubble of colored light, sometimes looking like an eye, sometimes like a flower, sometimes like a soap bubble caught in a beam of light. The Helix Nebula, sometimes called the Eye of God, is one of the closest to Earth, about 650 light-years away. It is a vast, concentric ring of gas, pale blue at its inner edge, deepening to red at its outer, with a tiny white dwarf star at its center, the exposed core of a star that once shone like our Sun, now cooling slowly in the dark. In about 5 billion years, the Sun will do exactly this. The Earth, or whatever remains of it after being engulfed by the expanding red giant phase, will become part of a nebula. The atoms of the Earth and of everything on it will drift outward into space, mixing with the interstellar medium, eventually becoming part of a new cloud, a new collapse, a new star. The universe does not waste material. It cycles everything. Stars are born from clouds. Stars die into clouds. Clouds become stars again. This cycle has been running for nearly 14 billion years, and every atom in your body has been through it at least once, probably several times. The iron in your blood was made in the core of a star many times larger than the Sun, forged under conditions of extreme heat and pressure, and then scattered across space when that star exploded. The calcium in your bones, the phosphorus in your DNA, the oxygen in every breath, all of it assembled in stellar cores, all of it released in stellar deaths, all of it drifting through the galaxy for billions of years before being swept up into the cloud that became our solar system, finding its way into the oceans of a young Earth, and from there over billions of years of chemistry and biology into you. You are not just looking at the universe from outside. You are made of it. You are it, turned inward, briefly aware. Let's rest with that idea for a moment, and then drift gently towards something even more philosophical: the fate of everything. The universe, as we currently understand it, has a long future ahead of it. But that future has a shape, and that shape changes slowly over timescales almost impossible to conceive. Right now, we live in what cosmologists sometimes call the stelliferous era, the age of stars. We are in the middle of a period stretching from roughly 100 million years after the Big Bang to perhaps 100 trillion years from now, during which stars form, burn, and die across the universe. It is, by some measures, the most active and luminous period the universe will ever experience. And we are in it. We exist during the universe's creative peak, the era when matter organizes itself into the most complex structures it will ever build: stars, galaxies, planets, and life. After the stelliferous era ends, when the last of the gas clouds have been used up, the last new stars have ignited, and the remaining stars are burning down like the final candles in a very large room, the universe will enter darker, quieter phases. The last stars to burn will be the smallest and most miserly, tiny red dwarfs, sipping their hydrogen fuel so carefully that they can shine for 10 trillion years. 10 trillion. By comparison, the current age of the universe is only 13.8 billion years. The red dwarfs will outlast us by a factor of 1,000. But even they will end, and when they do, the universe will enter the degenerate era, a long, dark period filled mostly with white dwarfs and neutron stars and black holes. No new light will be generated. The temperature of everything will drift toward absolute zero over unimaginably long timescales. Then the black holes will reign. One by one, the white dwarfs and neutron stars will decay, their matter slowly dissolving through quantum processes on timescales of 10 to the 34th power years, a number so large that writing it out would take more digits than there are atoms in the observable universe. Eventually, only black holes will remain, the last massive structures in an otherwise diffuse, cold, dark universe. And even those will end. Stephen Hawking predicted in 1974 that black holes are not truly permanent. They emit a faint, steady radiation, now called Hawking radiation, caused by quantum effects near the event horizon. Over time, this process causes them to slowly lose mass. A stellar mass black hole might take 10 to the 67th power years to evaporate completely. A supermassive black hole, like the one at the center of M87, might take 10 to the 100th power years. But eventually, given enough time, they too will go. The last black hole will release its final photon into an empty, cold universe. And then, a universe of nothing but diffuse particles and radiation, slowly expanding, growing colder, approaching, but never quite reaching absolute zero. This state, the heat death of the universe, is the current best guess for the ultimate fate of everything. It sounds bleak, and in some moods, it is bleak. But in another mood, the mood of a person lying in the dark, breathing slowly, feeling the warmth of their body and the softness of the surface beneath them. It is just a very long story with a very gentle ending. A universe that burns brilliantly for trillions of years, and then quietly, slowly, with great patience and no drama, goes still. That is not a bad way to end. And we are so early in that story that the ending is not something to fear or mourn. We are in the first chapters. The stars are bright. The galaxies are active. The universe is full of light and motion and complexity, and, in at least one small corner, full of creatures who lie awake at night wondering about all of it. That is extraordinary. Let's return, slowly and gently, to Saturn. Let's stay with it a little while longer before we say goodnight. When Voyager 1 flew past Saturn in November 1980, it sent back the first close-up images of the ring system in detail. Scientists who had spent careers studying Saturn through telescopes suddenly saw the rings up close, not as 2 or 3 broad bands, but as hundreds, thousands of individual ringlets, fine-structured like the grooves of a record album, intricate beyond anything previously imagined. And the moons. Saturn has more confirmed moons than any other planet in the solar system. At current count, well over 100, though many of them are small captured objects, chunks of rock or ice held in irregular orbits. The larger moons are worlds unto themselves. Titan is the largest of Saturn's moons, and one of the most extraordinary objects in the solar system. It is larger than the planet Mercury. It has a thick atmosphere, the only moon with a substantial atmosphere, made mostly of nitrogen with methane and other hydrocarbons. It has seasons. It has weather. It has rivers and lakes and seas, not of water, but of liquid methane and ethane, pooled in basins near the poles, fed by methane rain that falls from orange clouds. The Huygens probe, released by Cassini in 2005, descended through Titan's atmosphere for over 2 hours, transmitting data all the way down, and finally landed on the surface. It was the most distant landing ever achieved by a human-made object on another world. The surface, Huygens found, was a flat, dark plain of ice pebbles, worn smooth by flowing liquid, a beach-like surface beside a vanished methane sea. Enceladus is another wonder. A small, bright moon, only about 500 kilometers across, that should by all rights be a frozen, geologically dead ball of ice. But Cassini discovered something astonishing. At its south pole, enormous geysers are erupting. Columns of water vapor and ice particles are shooting hundreds of kilometers into space from cracks in the ice, called tiger stripes, driven by internal heat, possibly from tidal flexing caused by Saturn's gravity. Beneath Enceladus's icy crust, there is a liquid water ocean, a global ocean, with hydrothermal activity on its ocean floor, with all the ingredients, water, heat, organic chemistry, that we associate with the possibility of life. We have not found life on Enceladus. We don't know if there is any. But we know the conditions are right. And knowing that, somewhere in the dark ocean beneath the ice of a moon of Saturn, a moon orbiting the same ringed planet that Galileo couldn't quite understand, there might be something swimming, something metabolizing, something alive in its own quiet way. That possibility alone is one of the most astonishing things I can hold in my mind. Saturn, in other words, is not just a beautiful planet with elegant rings. It is a system, a solar system in miniature with its own collection of worlds, each strange, each specific, each full of questions we haven't answered yet. And the rings themselves, we now know, are probably the remnants of one of those worlds. A moon that ventured too close, or was struck by something, or was simply pulled apart by tidal forces over time and spread itself into the flat disk we see today. The rings are, in a sense, a moon that forgot how to be a moon and became something more diffuse, more ethereal, more like a garment around the planet than a companion. There is something almost tender about that reading of the story, a world that dissolved. And yet, the rings it became are among the most beautiful structures in the solar system. Perhaps dissolution in the right conditions can produce something more beautiful than the original. That thought can accompany you into sleep if you like. Think of today. Think of the things that came apart, the plans that didn't hold, the moments that dissolved before you could hold them, the things you let go of or that let go of you, and wonder whether they too might have scattered into something unexpected, something thin and wide and catching the light in ways you haven't seen yet. You don't need to resolve that thought. Just hold it lightly, the way you'd hold a snowflake, knowing it won't last, appreciating it anyway, letting it melt in its own time. The rings of Saturn are melting in their own time, falling gently into the planet below, becoming part of Saturn's atmosphere, mixing into the pale gold clouds, no longer separate, no longer catching the light as rings do. Transformed, but not gone. Changed, but not lost. Everything changes. Everything transforms. The universe is, at its core, a system for transforming things. Matter into energy, gas into stars, stars into nebulae, nebulae into new stars, and somewhere in the long middle of all that transformation, briefly, us. Briefly aware, briefly wondering, briefly here. And right now, you are here. Warm in the dark, breathing slowly, letting the day dissolve the way ring material dissolves. Slowly, gently, without drama. The concerns of the morning are already far away. The concerns of tomorrow haven't arrived yet. There is only this, the present moment, which is the only moment that ever actually exists, and which is extraordinarily quiet tonight. Feel your body, heavy and warm. Feel the support beneath you, mattress or chair or whatever holds you. Feel the air in your lungs and the slow release. You have been breathing all day without thinking about it, and your body will keep breathing all night while your conscious mind takes its rest. The universe breathes too, in its way. Galaxies contract and expand. Nebulae collapse and bloom. The cosmic microwave background, the faint afterglow of the Big Bang still permeating all of space in every direction, pulses with ancient information, a whisper from the very beginning of time, still traveling outward through the expanding universe, growing fainter with each passing billion years, but never quite disappearing. If you could hear it, it would sound something like the softest static imaginable. But behind that static, encoded in the frequencies, is the story of everything that ever happened. The geometry of the early universe, the seeds of every galaxy and star and planet that would ever exist, including this one, including you. You are part of that story. A late chapter written in a quiet corner, but a chapter nonetheless. Now let the story rest for tonight. Let the pages go still. The rings of Saturn are out there, catching the light of the distant sun, losing a little of themselves every second, impossibly beautiful in the darkness. Enceladus is erupting its quiet geysers into space. Titan is being rained on by methane. The Milky Way is rotating, its spiral arms moving in a slow, vast turning that takes hundreds of millions of years. 2 trillion galaxies are drifting in the expanding space, growing further apart, growing quieter. And in the dark between them, that vast, invisible ocean of dark energy and dark matter The universe is gently, persistently, doing something we don't yet understand. And somewhere in all of that, on a small planet orbiting an ordinary star in the outer arm of one ordinary galaxy, you are lying in the dark, eyes soft, breath slow, thoughts dissolving like snowflakes, like ring material, like the last light of a distant nebula. Rest now. You've come far enough tonight. Let sleep do what it does, dissolving the boundaries between things, carrying you somewhere wordless and warm, somewhere without timescales or light years or event horizons. Just the quiet dark and the slow breath and the body's deep knowledge of how to rest. The stars will be there when you wake. Saturn will still have its rings. For now, for 100 million years more, they'll be there, glittering quietly. The universe will be exactly where you left it. And in the morning, when the light comes back and the day begins again, you will carry with you, somewhere beneath the noise of ordinary life, the memory of having traveled here, of having floated briefly in the vast dark between the stars, of having remembered for a little while how large and old and patient everything is, and how in the middle of all that enormousness you exist, specific and brief and real. That is enough. That is more than enough. Good night, dear traveler. Good night from Dreams of Gravity. From wherever these words found you tonight, whatever city, whatever season, whatever time, I hope the night is gentle with you. I hope your sleep is deep and full of soft light, full of the kind of dreams that feel like traveling, like floating, like being very far from any worry. Dream of rings of ice in golden light. Dream of galaxies turning like slow music. Dream of new stars being born in quiet clouds, unhurried, certain, burning their first light into the dark. Dream of the universe at rest. Good night.